Today, we're taking on something huge, the very ideas of space and time. We're going to dismantle how you probably think about them.
Yeah, it's quite a journey. Our sources map out this, well, 400-year evolution in physics,
Yeah.
moving from a really solid, intuitive picture of the universe.
Like a stage, right?
Exactly, a fixed stage.
Yeah.
To something much weirder, dynamic, maybe multidimensional, maybe not even real at the deepest level. The goal here is for you to really grasp this radical shift.
I like how the research frames it, this idea that our basic perception is like looking at a masterpiece painting through the bottom of a Coke bottle, just completely distorted.
Right, physics has constantly challenged that common sense view. And the big debate, swinging back and forth, has always been, is space a real thing? An entity.
Or just a way we talk about where things are relative to each other, an abstract idea.
Precisely. That pendulum swing is what we're tracing, starting way back with Isaac Newton.
Okay, so Newton. His physics felt so right, didn't it? The maths lined up perfectly with everyday experience pushing things, gravity working predictably. It gave a solid footing to intuition.
It did. But for that maths to work, Newton needed a foundation. He proposed that space itself was real, unchanging, and absolute arena, basically.
Wow.
Empty, transparent. He called it absolute space.
Absolute space. And wasn't there a kind of almost spiritual dimension to this for him?
Yes, definitely. He linked it to the sensorium god. The idea, drawing from others like Henry Moore, was that even empty space wasn't truly empty. It was filled with divine presence, the medium through which God perceived the universe.
But how do you actually prove something like that exists in an invisible absolute container?
Well, he had a clever demonstration. The spinning bucket experiment.
Right, the bucket of water.
Exactly. You spin a bucket filled with water. At first, the water's flat. Then, if the bucket spins it up, the water surface becomes concave, climbing the walls. But here's the key part. Even if you stop the bucket, the water stays concave for a bit while it's still spinning, relative to what?
Relative to absolute space.
That was Newton's argument. The concave shape wasn't just about the bucket. It was evidence of acceleration against this ultimate fixed background. Proof that absolute space was real.
That's pretty ingenious, actually. A tangible effect from an invisible cause. But that wasn't the end of the story, was it?
Not at all. Much later, the Austrian physicist Ernst Mach came along and questioned that whole line of reasoning.
Mach, he had a very different take.
A completely relational view. Mach said, look, motion, acceleration, these things only mean something relative to other physical things. The walls of the lab, the earth, the distant stars, material benchmarks.
So no absolute reference frame needed.
He argued not. He came up with this brilliant thought experiment. Imagine Newton's spinning bucket, but in a universe that's completely empty otherwise, just total blackness, no stars, nothing.
Okay, an empty universe.
Mach reasoned the water surface would stay perfectly flat. Why? Because with no external reference points, what would spinning even mean? How would the water know it's spinning?
It would be indistinguishable from just sitting still.
Exactly. Motion only has meaning relative to the other stuff in the universe. This idea that the inertia of an object, its resistance to acceleration, is somehow determined by all the matter scattered across the cosmos. That was Mach's principle.
Now, didn't Einstein later show that space-time is a thing, sort of vindicating Newton in a way? So why was Mach still so important?
Oh, hugely important, because he shifted the focus. He pushed physics towards thinking about what's actually observable and verifiable, and that core idea that the behavior of local matter is influenced by the large-scale distribution of mass in the universe that deeply influenced Einstein when he developed general relativity is a crucial stepping stone.
Which brings us neatly to Einstein, 1905, special relativity. This just blows everything up, doesn't it? It killed the old ether idea.
Right, the supposed medium that light waves travel through. Gone.
And it forced space and time together, no longer separate things.
Absolutely. The biggest casualty was the idea of absolute independent space and absolute universal time. They got fused into one four-dimensional framework, space-time. It's a single entity.
And how we experience that entity depends on our motion.
Precisely. What looks like pure space to me might look like a mix of space and time to you if you're moving relative to me.
The sources use that analogy. I like space-time isn't like flipping through still photos in a book. It's more like a loaf of bread.
Yes, a big loaf of space-time. It's a great way to visualize the relativity of simultaneity. Think of now your present moment across all of space as a slice through that loaf.
Okay, my slice.
But someone moving relative to you slices that same loaf at a different angle. There now is a different cut.
So they literally disagree on what events are happening simultaneously across the universe.
Fundamentally, your now is not my now
Yeah.
if we're moving relative to each other. The concept of a single universal now that everyone shares, it's an illusion based on our slow speeds and small distances.
And this isn't just some tiny effects, is it, over cosmic distances?
It becomes mind-boggling. The example given is powerful. Imagine someone 100 trillion miles away. If they start walking towards you at just, say, 10 miles per hour, a completely trivial speed,
Yeah.
their angled slice of now, because of that vast distance, cuts so differently through the space-time loaf that it includes events on Earth that are, from your perspective, maybe 150 years in the future.
Wait, what? So for them, something happening here in 2170-something has already happened in there now.
According to their frame of reference, yes. Some future election, some future event. It's already in their present moment, even though you haven't experienced it yet. That's how profoundly relativity reshaped our understanding.
That really does demolish common sense. Okay, so that's special relativity. Then came general relativity about 10 years later.
Right. GR took it further. It wasn't just about motion, it was about gravity. Einstein showed that gravity isn't a force pulling things across space, like Newton thought.
It's the shape of space-time itself.
Exactly. Mass and energy actually warp and curve the fabric of space-time around them. And what we feel as gravity is just us moving along those curves. Space-time isn't passive, it's dynamic, it participates.
And this solved another problem with Newton's gravity, right? The speed thing.
Yes. Newton's gravity had to act instantaneously across any distance. If the sun vanished, Earth should instantly fly off. But special relativity said nothing. Not even gravity can go faster than light.
So GR fixed that.
It did. General relativity showed that these warps and ripples in space-time gravity waves travel at exactly the speed of light. Problem solved.
And going back to Mach for a second, did GR incorporate any of his ideas, even though it does have space-time as a real thing?
It did, in a subtle but important way. While GR allows acceleration relative to space-time itself, disagreeing with Mach's purely relational view, the actual geometry of space-time, the gravitational field that defines that acceleration, well, it arises from the sum total of all the mass and energy distributed throughout the entire cosmos.
Ah, so the distant stars do matter, just in a different way than Mach originally thought.
Precisely. The large-scale structure influences the local geometry. So Mach's insight echoes within Einstein's framework.
Okay, so Einstein paints this amazing picture of dynamic space-time, but then quantum mechanics arrives on the scene, and the two theories just don't play nicely together, do they?
They really don't. That's arguably the biggest challenge in physics today. General relativity describes a smooth, flexible space-time. Quantum mechanics, on the other hand, typically assumes a fixed, rigid background stage for particles to interact on.
Dynamic stuff on a static stage versus dynamic stuff in a dynamic stage.
You've got it. They have fundamentally different descriptions of the arena of reality. And this clash forces other weird things upon us, like abandoning strict determinism. Well, classical physics, Newton's world, is deterministic. If you knew the exact position and velocity of every particle now, you could calculate the entire past and future. Perfect prediction, in principle. Quantum mechanics says no. The best you can ever do is calculate the probability of finding a particle here or there, or having this or that property. Randomness, chance, seems to be baked into the fundamental workings of the universe.
And then there's the really spooky stuff, non-locality.
Ah, yes, quantum entanglement. This might be the strangest departure from intuition. It shows that distance doesn't guarantee separation or independence.
So you can have two particles linked?
Linked in a deep quantum way. You can create a pair of particles, say, photons, that are entangled. Then you send them in opposite directions, even light years apart.
Okay.
When you measure a property of one particle, say, its polarization, you instantaneously influence the corresponding property of the other particle, no matter how far away it is.
Instantaneously, like faster than light.
The influence appears instantaneous. It's as if the space between them just doesn't matter for this connection.
Now, Einstein famously hated this, right? He called it spooky action at a distance. He, Podolsky, and Rosen wrote that EPR paper arguing quantum mechanics must be incomplete.
They did. They suspected there were hidden variables, like pre-programmed instructions. Their analogy was like having a pair of gloves. You put one in each box, send them far apart. When you open yours and find a left glove,
you instantly know the other is a right glove. No spooky connection needed, just prior correlation.
Exactly. That's what EPR hoped was going on. But then came John Bell.
Bell's theorem.
Bell figured out a way to experimentally test whether it was like The gloves, local hidden variables, or something genuinely weirder. And the experiments have been done many times now.
And the result?
The universe is weirder. The correlations between entangled particles are stronger than any local pre-programmed theory like the gloves could explain. The particles don't seem to have definite properties until measured, but the random outcomes are still instantly correlated, the most straightforward interpretation. Our universe is non-local. Space doesn't always separate.
But wait, if measuring one instantly affects the other one light years away, doesn't that violate Einstein's speed limit? Can't we use this to send faster than light signals?
Ah, the crucial question. And the surprising answer is no, you can't.
Why not?
Because while the correlation is instantaneous, the outcome of any individual measurement on either particle is fundamentally random. You can't control whether your particle will be spin up or spin down, or horizontally or vertically polarized.
So I can't force my particle into a state to send a coded 1 or 0 to my friend instantly.
Exactly. You only discover the correlation after the fact when you compare your random results with your friend's random results using some conventional, slower-than-light communication method, like a phone call or email. So no information is transferred faster than light. Special relativity is safe.
Okay, that's subtle. The connection is real and instant, but you can't use it to signal. Wow. Spooky, but not useful spooky for communication.
Right, and the weirdness doesn't stop there. As we move into the 21st century, even the concept of empty space gets overhauled again. The quiet Newtonian void is long gone.
Because of quantum uncertainty.
Yeah, quantum field theory tells us that even a perfect vacuum isn't truly empty or calm. It's a bubbling, frothing sea of activity vacuum fluctuations. Virtual particles and antiparticles are constantly popping into existence and annihilating each other in incredibly short times.
And this isn't just theory. We can actually detect this.
We can. The Casimir effect is direct evidence. If you place two uncharged metal plates incredibly close together in a vacuum, the quantum fluctuations between the plates are slightly suppressed compared to the fluctuations outside. This imbalance creates a tiny but measurable force pushing the plates together. Empty space has energy and exerts pressure.
So space is filled with stuff, fields, kind of like the old aether idea coming back.
In a way, yes, but crucially different. Space is permeated by various quantum fields. The Higgs field, for example, is everywhere, and particles interacting with it gain mass. But unlike the old aether, these fields are consistent with relativity. They don't define a preferred frame of reference or mess with the speed of light.
Okay, so empty space isn't empty. But then there's the really big component of space we haven't talked about, the dark universe.
Ah, yes. The elephant in the cosmic room.
Yeah.
In 1998, astronomers studying distant supernovae got a huge shock. They expected to see the universe's expansion slowing down due to gravity.
But they saw the opposite.
Exactly. The expansion is accelerating, speeding up. Something is pushing the universe apart.
And that something is dark energy.
That's the name we give it. Dark energy. It seems to be a property of space itself, a kind of intrinsic energy density that exerts a repulsive force and anti-gravity, essentially, like Einstein's old cosmological constant, maybe.
And the amount of this stuff is staggering.
Completely dominant. When cosmologists tally up the total mass energy budget of the universe, the ordinary matter that makes up you, me, planets, stars, all of that is only about 5%.
Just 5%.
Then there's dark matter, another mysterious invisible substance detected by its gravity, making up about 25%, which leaves dark energy accounting for the remaining 70%. 70% of the universe is this unknown energy driving cosmic acceleration.
So 95% of the universe is stuff we can't see and don't really understand.
Pretty much. We're like, as the sources say, flotsam on the cosmic ocean. Our existence is almost irrelevant to the universe's overall dynamics. It's profoundly humbling.
It really is. Okay, so we have this dark energy-filled space, quantum jitters. What about the structure of space itself? Are 3 dimensions all there is?
Well, leading theories like string theory suggest probably not. To make the mathematics consistent, string theory typically requires extra spatial dimensions, maybe 9 or 10 in total.
10 dimensions. Where are the other 6 or 7?
The idea is they're curled up incredibly tiny, compacted down to sizes far smaller than we can probe experimentally. So we only experience the 3 large spatial dimensions plus time.
And this leads to ideas like the brain world.
Right, the brain world scenario. It comes out of M theory, an extension of string theory. The idea is that our entire observable universe, All the particles and forces we know, except gravity, might be confined to a three-dimensional membrane or brain.
Like a sheet of paper floating in a higher dimensional space.
Sort of, yeah. A three-brain floating in higher dimensional bulk. Our stuff is stuck to the brain, but gravity, being related to space-time geometry itself, might be able to leak or spill out into those extra dimensions.
Could that explain why gravity seems so much weaker than the other forces? Like electromagnetism?
That's one of the main motivations for the idea, yes. Gravity's influence gets diluted across the extra dimensions.
While, okay, so extra dimensions, dark energy. We're getting pretty far from Newton's simple arena. What's the final frontier in demolishing space and time?
It's the idea that maybe space-time isn't fundamental at all. Maybe it's an emergent property, an approximation.
Emergent, like how wetness emerges from H2O molecules, even though a single molecule isn't wet?
Exactly like that. Perhaps space-time is a kind of collective statistical average of some deeper underlying reality that isn't spatial or temporal at all. Like talking about the average family having 2.2 kids, useful statistically. But no actual family is like that. Space-time might be a macroscopic approximation.
And the holographic principle hints at this too.
Strongly hints, yes. The holographic principle arose from studying black holes. It turns out the maximum amount of information, or entropy, you can pack into a region of space isn't proportional to its volume, as you'd expect.
But to its surface area, a 2D measure.
Yes, it's as if all the information needed to describe the 3D interior is somehow encoded on the 2D boundaries surrounding it.
Like a hologram stores a 3D image on a 2D film.
Precisely. This led to the conjecture that maybe our entire 3D universe is just a holographic projection of physical processes happening on some distant lower dimensional surface. Our perception of 3D space could be an illusion generated by underlying 2D physics.
Wow. Okay, let's try and recap this demolition job. We went from Newton's absolute fixed stage
To Einstein's dynamic, flexible space-time, where space and time are relative and warped by gravity.
Then quantum mechanics introduced randomness and spooky non-local connections, challenging spatial separation.
Followed by the discovery of a universe dominated by mysterious dark energy and dark matter, hinting at extra dimensions.
And ending with the possibility that space-time itself is just a convenient illusion, a hologram projected from a deeper reality.
It's an incredible intellectual journey. And understanding it matters because it fundamentally changes how we perceive reality and our place in it. That feeling of here and now might be much more subjective and less fundamental than we ever imagined.
So the final thought to leave you with, as physics grapples with unifying gravity and quantum mechanics, is that down at the tiniest possible scales, the Planck scale, space-time is thought to become this chaotic quantum foam where our usual notions of distance and duration completely dissolve.
Which leads to that ultimate question. Are space and time real fundamental building blocks of the cosmos? Or are they just incredibly effective tools, emergent concepts our minds use to make sense of a universe that, at its core, might be something entirely beyond space and time?